We have discussed this topic now in many contexts in terms of the record warming of 2023 and 2024, about whether we crossed 1.5 degrees C already in terms of a global mean temperature, and whether 2023 was so warm just because of an El Nino combining with the global warming, and said no, maybe the underwater volcano eruption in 2022, the Hanga Tonga High Pi, contributed as well, maybe cleaner air did, and so on and so forth. But what about the El Nino itself? Was it really different from other El Ninos in the way it grew and how warm it got and how it followed the big El Nino of 2015, 2016? The time difference between two big El Ninos tends to be about 15 years, but this one happened very quickly. So this paper is a nice paper that goes into details about what was different, and they use a lot of model experiments to explain the differences. And obviously once something happens, then you can explain it easily. If you predicted well, for example, 2023 El Nino was predicted far ahead of time and very well. So how did the models get it right then? Did they also do things the same way? So those are the kind of interesting issues that we always do in a post-mortem of an event after it happens. So strong 2023-24 El Nino generated by ocean dynamics. So it's a definitive statement that in general we have something called the Bjerknes feedback, where in the mean state the eastern Pacific around Galapagos is cold, in the west around New Guinea, Australia it's warm, so you have a sea surface temperature gradient, trade winds, and if for some reason, let's say the colder temperatures become warmer, the cold temperatures become a little bit warmer, let's say because trade winds relaxed or some wave came from the west and pushed the thermocline down, then you change the temperature gradient and you weaken the winds further, which reduces the upwelling further, which reduces the gradient further. So you have a positive feedback, which we call Bjerknes feedback, which is generally a critical part of the El Nino cycle as a whole. So what this paper is all about is to see how this behaved differently. Let's read the abstract and then some details. Globally, 2023 was the hottest year on record and saw the development of a strong El Nino with widespread impacts. This El Nino event was unusual for its strong oceanic warming, yet muted southern oscillation and wind anomalies over the tropical Pacific. So as I said, El Ninos have a very characteristic wind changes, but also remember southern oscillation is the pressure difference between Darwin and Tahiti, which was discovered by Gilbert Walker much before the Bjerknes feedback came along, almost half a century or longer later. Then we realized southern oscillation and the El Nino are basically the same thing. They are closely related, but this one is arguing that this phenomenon of the 2023 El Nino happened somewhat differently, that the pressure oscillation was not as tightly coupled to the El Nino itself because of the ocean warming. Okay, so this discrepancy is perplexing given the historical close coupling of El Nino and the southern oscillation. Atmospheric model experiments show that warming in the Atlantic and Indian Oceans in 2023 and the slow background sea surface temperature trend reduced the surface wind response over the tropical Pacific by modulating the Walker circulation. So we are reaching now for pan-tropical teleconnections or feedbacks to the El Nino. So we are saying warming in the Atlantic and the Indian Ocean in 2023 because of the massive warming we had. Typically El Nino itself is a mini global warming and it adds to global warming. But here we are saying there was already some warming that is unrelated to El Nino, and El Nino fed on these warmings. The slow background sea surface temperature trend reduced the surface wind response over the tropical Pacific by modulating the Walker circulation, which is the rising motion over the maritime continent, sinking motions over the East Pacific and West Indian Ocean and so on. We developed a hindcast system that reproduces 87% of the June to December El Nino warming even without wind stress feedback after 2023. So they take the model and tweak the feedbacks and say even without the wind feedbacks that we talked about in the Bjerknes feedback context, wasn't needed for this El Nino. The intense ocean warming was primarily driven by the strong buildup of Western Pacific heat content during the preceding prolonged La Nina, which lasted for 3 years. This indicates that the 2023-24 El Nino primarily arose from oceanic processes independent of the classic positive Bjerknes feedback mechanism. Due to the strong ocean memory, this event was highly predictable at long lead times, so presumably that's what the models got right. Climate model simulations suggest that such 2023 like El Ninos may become more frequent in a warming climate. So we always jump to this at the end, even though we haven't explained El Nino changes so far where warming has happened, but we love to say this may happen. So likely to happen. Is it necessary to say it? Well, why not? But scientifically we have to be sure that such statements are robust enough to put them in the papers, right? So let's look at some figures. I'm jumping ahead, it's a long paper, I'm going to be very brief. So sea surface temperature and sea level anomalies for 2023-2024 El Nino, obviously warm, but you can see it's warm all over, even off equatorial regions and also Gulf of Mexico here, and this is from comparable El Ninos compared to 2023-2024 El Nino. You typically get this dipole-like pattern, warm temperatures here and higher sea levels anomalies, and cooler temperatures and lower sea level anomalies. Okay, so if you look at mean mean sea level pressure and winds for 2023-24 El Nino, westerlies here, kind of disorganized trade wind anomalies, but you have clearly higher, so you have to be careful here, pressure anomalies, warm temperatures, lower SLP anomalies, cooler temperatures, higher SLP anomalies. That's consistent. But if you look at the comparable El Ninos, there's a much clearer structure in terms of the scales and the east-west contrast. So you can see wind response is very different compared to what you expect for a similar magnitude of El Nino. So here you are looking at surface winds at 10 meters and Nino 3 SST anomalies, and there is a very strong correlation with the 23 El Nino falling here compared to 82-83, which was big, 2015-16, 97-98, which was big, and the smaller events tend to be spread around. And of course here we are in the La Nina regime with negative Nino 3.4, Nino 3 sea surface temperature anomalies, which is average of 5 south, 5 north, and a box that's in the central west eastern Pacific. And if you look at again Nino 3 SSTA versus Southern Oscillation Index, also a fairly strong correlation, but 82-83 was on this side in terms of a correlation, and 23 was here, which is, you know, again different from 2015 and 1997. So was this also discussed in a similar way? Yes, it was discussed a lot because it was one of the best recorded big El Ninos of the time, a lot of papers, but this particular point about it being different in terms of the feedbacks and winds was not necessarily discussed. So keeping that in mind, lots of details on the model experiments and evolution of the El Nino. You are now looking at the so-called Hofmüller diagrams, where you are going from west to east, and you are looking at rainfall anomalies and wind stress anomalies. You are going from year 0 into year 1. So the strong westerly wind anomalies are always part of the El Ninos. Comparable El Ninos here have much different structure. These become so-called multiplicative noise, where the westerly wind bursts push the convection towards the east. Their fetch and duration can begin to increase, as you can see, may have started as small events and then slowly becomes larger, whereas this doesn't have such a systematic structure here compared to this, and rainfall anomalies are also very different here. Okay, so here again SLA and SSTA again different compared to other El Ninos. See the subsurface temperature structure. You can see that the 2023-24 El Nino actually had a little pool of cold water just below the surface here, whereas strong El Ninos typically tend to have the warm waters spreading all the way from the west to the east in a so-called discharge state. So a lot of the technical terms I'm using, they are in many of my El Nino podcasts that you can follow up with, even Bieknes feedback podcast and so on and so forth. So here I'm assuming you are aware of what is recharge, discharge, and what is a discharge, and so on and so forth. Okay, so equatorial temperature, April to October 2023-24, comparable El Ninos, they say in US, we say comparable El Ninos. You can typically see it's exhausted warm pool here with colder anomalies, and here warmer anomalies, whereas this one, because of the ocean warming, had warm anomalies all across. So the pattern itself we have discussed elsewhere. I was part of a paper led by Ashok Karmuri where we said this is actually a combination of global warming and El Nino. So this cooler temperature on the west is probably disappearing because warming rates here are very high. So you are superposing the El Nino life cycle on top of global warming as well, which is approximately what this paper is saying. But this is also talking about the consequences of that in terms of the wind response and the coupled response of the El Nino itself. Okay, so this is the November, December, January. This is April to October. But you can see by the end of the El Nino, it was beginning to look similar with the exhausted temperatures here, even though it was weaker than the cooler temperatures you see typical comparable El Ninos. Typically here we are talking about 82, 83, 97, 98 and 15, 16. They are strong El Ninos, so strong warming here, strong cooling here, whereas this one had relatively weaker warming and weaker cooling as well. Okay, so the AGCM, atmospheric general circulation model experiments, basically confirm, I'm not going to go into details. They have a control run which reproduces 87% of the warming when they give it the sea surface temperature information, because when you do atmospheric general circulation model experiments, you have to prescribe the ocean in terms of sea surface temperatures. Sometimes you have a mixed layer, in which case you are giving heat content and heat transport and so on and so forth. So the sensitivity experiment is basically where you use the Pacific only, Indian and Atlantic warming as well, and include the trend. So Hofmuller diagram of equatorial zonal wind stress anomalies in color shading from the control run, Pacific run, Indian and Atlantic run, and the trend run. Okay, so the associated June-December averaged vertical velocity, which gives you strength of the convection. So no, they are talking about the, yeah, it's the atmosphere. You are going from the surface into the upper atmosphere. So you can basically re-emphasize the points that the warming of the Indian and Atlantic Oceans perturbed the entire Walker cell, and that allowed the 2023-24 El Nino to evolve without having this Bieknes feedback and the role of the ocean in the classic way with Bieknes feedback, but happened mostly with ocean's role, but coming through Indian and Atlantic Oceans. Okay, so this is a figure with lots of information as well, and you can see in the control run and observations, the argument is that their experiment is producing the results fairly well, so you can trust the analysis. So they are doing the initial conditions of April 2023. They are able to predict it fairly well, but if they use winds from 2023, you can see that the evolution in terms of SST anomalies adds. So basically you can add and subtract the impacts of the Indian Ocean. I'm being incredibly lazy here, but I just want to stick to the main point. And let's read the caption just to be sure. Impacts of ocean initial conditions and wind stress anomalies on the 2023-24 El Nino and other three comparable El Ninos. So they are also offering comparable El Ninos for other El Ninos to argue that the entire coupled response was different, hence subsurface variability evolution during El Nino itself was also different. Here simulated control run and observed Nino 3 SSTAs looking very good. from 1982 to 2023, so they covered the strong events. B simulated Nino 3.4, Nino 3, sorry, SSTAs from control in it April 2023 and their difference. Okay, so that's wind 2023. So this is the difference of the evolution, sorry, not the initial conditions. And so it's always good to read. I read it, but then I forgot. Okay, it's always interesting to read a paper and think this is exciting, I should record it, and then you forget some of the details because I read it and then I wait till I get time to record the podcast. But anyway, similar to B, but for the composite of the other comparable El Niños, so you can see that the difference is very, the wind differences between the control run and the initial conditions of April 2023 versus other El Niños is very different here. Okay, that's just re-emphasizing the point with the model, saying in data you can diagnose that Indian and Atlantic Oceans played a role, but to show that that actually happened, you need these kind of sensitivity experiments, basically, right? The solid lines in B and C indicate ensemble mean, so there are some details. They do multiple realizations just to make sure the robustness of the results. D, horizontal distributions of sea level anomalies and SSTA here. Okay, so you can see sea surface temperatures 2023, so sea level JFM, sea level anomalies and SSTA, so other El Niños and 2023-24. You can see the difference in the structures. Their focus is mostly in the deep tropics, but you can see there are other differences as well. This is sea level anomalies and SSTA. Now you are looking at Hofmüller diagram again going from west to east, and you can see how things evolved. It's very different for the 2023 El Nino compared to the other El Ninos. So it's still basically the same ideas. What are the insights on ENSO dynamics from this study? Statistical analysis of historical events has led to important advances in understanding the coupled dynamics of El Niños and its flavors. When we say flavors, the warming doesn't always happen on the east. Which figure should I use? Let's say this one. You sometimes get cool temperatures here and warming happening here, which we call dateline El Niños or Central Pacific El Niños. So we call them ENSO diversity or ENSO flavors. Okay. Our observational analysis has shown that the 2023-24 El Nino was peculiar. The atmospheric response to the strong equatorial Pacific SSTs were weak compared to those inferred from historical events. This suggests that the Bjerknes feedback was not fully established to promote the growth of this strong El Nino, and a surprising result against this is a surprising result against a widely accepted ENSO theory that centers on this coupled feedback mechanism. Amy Clement already had some papers arguing that you can have just thermodynamic coupling without this Bjerknes dynamic coupling and still get El Ninos, and this goes in a similar line, except with a real example as well. Through advanced GCM experiments, we show that even in the absence of tropical AFC feedbacks or the Southern Ocean component, ocean dynamics alone can generate a strong El Nino. Our AGCM results reveal that strong tropical interbasin impacts played a vital role in reducing the atmospheric anomalies over the tropical Pacific Ocean during 2023. Specifically, both the record-breaking warmth of the tropical Atlantic and Western Indian Oceans in 2023 and the tropical long-term SST trends induced anomalous water circulation subsidence and easterly surface wind anomalies over the central and eastern Pacific. These influences moderated the tropical atmospheric perturbations associated with the developing El Nino, preventing the full establishment of the Bjerknes feedback during this event. Okay. The 2023-24 El Nino illustrates that ENSO is not a phenomenon confined to the tropical Pacific basin, which we already looked at, but can be strongly modulated by SST conditions in other tropical basins. This raises an important question of whether a single El Nino index, for example, 3.4 SST, is a good measure of global atmospheric anomalies, for example, the SO. The bottom panels of Figure 1 show that the answer is yes for a statistically average typical El Nino event, ENSO event, but individual events require a close look, as we did here for the 2023-24 El Nino. Whether that will increase predictability and teleconnection understanding, etc., has to be looked at further. We have developed an improved ocean hindcast system for forcing the ocean component in a GCM with observed wind stress. This enables us to uncover the key physical processes underlying the strong oceanic warming despite weak Beekner's feedback during this El Nino. So I skipped many of those modeling details, but you can go back and read the paper. We show that the unprecedented buildup of the ocean heat content is seen in the sea level anomaly in the tropical western Pacific Ocean following a long-lasting La Nina drives SST warming in the eastern Pacific through downwelling Kelvin waves. So you have loaded the system, the tilt is very high, east is shallower, west is deeper, and then you set off the waves, and then the system oscillates or goes into a El Nino mode. As the trade winds returned to their climatological values in the decaying La Nina, downwelling Kelvin waves induced large subsurface warming in the eastern equatorial Pacific Ocean and raised SSTs through thermocline feedback. Wind stress anomalies, which have been widely considered essential in El Nino dynamics, played a secondary role in the development of the 2023-24 event. So is this just in the range of Beekner's feedback being very weak compared to other events where it is strong? Or is it really a very different process? Due to the memory of the large ocean heat content anomalies in the Western Pacific, the North American multi-model ensemble consistently predicted Nino 3.4 warming of about 1 degree C as early as January to March of 2023, which is usually a harder time to predict El Ninos because you have to get past the spring, and we have something called a spring predictability barrier, and so on and so forth. So that's what they mention here, that this early forecast went across the so-called spring predictability barrier. Climate models project that occurrences of 2023 like El Nino increase markedly in future warmer climate, primarily due to more frequent strong positive SLA events in the Western Pacific. These stronger SLA results from a more pronounced sea level response to wind stress, which is basically also a heat content gradient, potentially linked to the factors such as reduced wave damping due to faster phase speeds from enhanced vertical stratification, or the nonlinear thermal expansion of seawater. Okay, reduced wave damping due to faster phase speeds. So obviously waves in the ocean depend very much on density, and which depends on stratification or gradients of density. Further research is required to better understand the underlying physical processes. So you can say that if people had already said this will happen and this happened, then 2023-24 El Nino gives us a glimpse of how the warming projections may be holding true in some cases. There are lots of biases, uncertainties, issues, but nonetheless, when you get a positive validation, it's always great. But considering El Ninos happen very infrequently, 2 to 4 years, and each El Nino tends to look very different, we may not see another similar process of, weak Beekner's feedback with impacts from Indian and Atlantic Oceans happening anytime soon. But it may also happen because Indian Ocean is rapidly warming, and so on and so forth. So it's a nice story, and I notice again that I always say so on and so forth, that a little too often, but nonetheless, see you in the next topic.